Would a rose by any embedding smell as sweet? Large language models, or LLMs, are often criticized for lacking true understanding and inability to reason with their knowledge. They are seen merely as advanced autocomplete systems. We believe that this perspective might be missing an important insight. We suggest that LLMs do develop a kind of empirical understanding that is similar to geometry, which seems quite sufficient for a range of applications in natural language processing, computer vision, coding assistance, and so on. However, this geometric understanding, built from incomplete and noisy data, makes them unreliable, difficult to generalize, and lacking in inference capabilities and explanations. This is similar to the challenges faced by heuristic-based expert systems decades ago. To overcome these limitations, we suggest that LLMs should be integrated with an algebraic representation of knowledge that includes symbolic AI elements used in expert systems. This integration aims to create large knowledge models, or LLMs, that not only possess deep knowledge grounded in first principles, but also have the ability to reason and explain, mimicking human expert capabilities. To harness the full potential of generative AI safely and effectively, a paradigm shift from LLMs to the more comprehensive LLMs is needed. Introduction. What's in a name? That we call a rose by any other name would smell as sweet. These immortal words from Shakespeare's Romeo and Juliet resonate in the context of large language models. One might ask, what's in an embedding? Would a rose by any embedding still smell as sweet? In other words, does an embedding capture all the properties of an entity comprehensively? Related to this is the important question: do LLMs truly understand the meaning of the words and sentences they generate as humans do, or are they merely performing autocomplete without any understanding? In this paper, we address these questions from the perspective of knowledge representation in artificial intelligence. A tale of two representations: algebra versus geometry. Vector embedding of tokens in a large language model is a type of knowledge representation. A well-known example of the importance of knowledge representation in problem solving is the difference between Indo-Arabic and Roman numeral representations of numbers. Roman numerals might be great for numbering Super Bowls, but they are a nightmare when it comes to doing math. A good knowledge representation should make features that are central to problem solving obvious and easy to manipulate, which is what the Indo-Arabic decimal number system does for arithmetic. Another interesting example is the Hindu monk problem. One morning, a monk sets out at sunrise to climb a path up the mountain to reach the temple at the top. He arrives at the temple just before sunset. A few days later, he leaves the temple at sunrise to descend the mountain, traveling faster since it is downhill. Along the way, in both his upward and downward journey, he rests at different spots at different times briefly. Is there a spot along the path that the monk will occupy at precisely the same time of day on both trips? Knowledge representation is key to solving this problem. Thinking about the problem verbally or in terms of rates and distances is unproductive. It is nearly impossible to solve the problem this way. However, it is easily solved by visualizing the problem. Imagine the monk's image on the path ascending the mountain, starting at dawn. At the same time, imagine another image of the monk on the same path descending the mountain, also starting at dawn. The two images will meet somewhere on the trail and therefore occupy the same spot at the same time of day. The problem that is virtually impossible to solve in the verbal representation is solved easily in the visual representation. The visual representation makes this central feature explicit and easy to manipulate. Both the Indo-Arabic numerals and visual representation make important features of the problem obvious and easy to manipulate, thereby making reasoning much easier. This is central to many problem-solving tasks. Now, let us consider the algebraic versus the geometric representation of mathematical objects, such as a circle. In algebra, a circle of radius 1 whose center is at the coordinates 0, is given by the equation x squared plus y squared equals 1. The geometric representation of the same circle is seen in the figures provided. One figure shows a circle with radius 1, and another shows a circle with angular information, or 360 degrees, explicitly marked. Now, let us perform a thought experiment. Consider two individuals, Alice, who is familiar only with the algebraic representation of a circle, and Georgette, who understands only the geometric representation. Who truly knows or understands the circle better? Whose representation is more comprehensive? It depends on the questions they are asked. Consider the following questions. Are points A at coordinates 0.8, 0.6, and B at coordinates negative 0.8, negative 0.6 on the circumference of the circle? Are these points close to each other or far apart? Are they on opposite ends of the circle? What is the angle subtended by the point C at coordinates 0.8, 66, 0.5, and D at coordinates negative 0.342, 0.94? To answer these questions, Alice, using only algebraic reasoning, will have to first substitute these coordinates into the equation to verify whether they lie on the circumference. Then, to find out whether they are close or far, and whether they lie at opposite ends, she will have to calculate the arc length between the points, which would require some additional computations and analytical reasoning. On the other hand, Georgette would merely locate the points A and B in her geometric representation of the circle, and mere inspection tells her that they are on the circumference, that they are far apart, and that they are on opposite ends of the circle. Using the geometric representation, she can see that the angle subtended between points C and D is 80 degrees. All this requires no reasoning at all. The answers are obvious and are simply looked up. Georgette doesn't reason because she doesn't have to. The questions that require some analytical effort on the part of Alice are effortless for Georgette. Like the Hindu monk problem, the representation makes all the difference. A picture is worth 1,000 words indeed. So, when one asks Georgette for an explanation about how she reached her conclusions, her answer might be something like, points A and B are on the circle because they are, and I can see that they are on opposite ends and that the angle between them is 80 degrees. There is no need to explain any of this. She cannot explain her conclusions to anyone who does not have access to her representation. Let us consider one final example. Consider two circles given by the equations x squared plus y squared equals 4 and x minus 1.5 squared plus y minus 1 squared equals 1. Do these circles intersect? If so, what are the intersection points? For Georgette, the answers are trivial. She sees from the figure that the intersecting points are approximately 0.89, 1.79, and 2.00, 0.130. However, to arrive at the same results using the algebraic representation, Alice will have to do some analytical reasoning and computation. Thus, the geometric rows smell sweeter than the algebraic rows in these situations. Now, let us turn the tables and ask a different kind of question. What is the representation of a circle in 3 and higher dimensional spaces? What are the surface area and volume of a 3-dimensional circle, that is, a sphere? As we know, these questions cannot be answered using the 2-dimensional geometric representation of a circle. We will need additional data to show the sphere in 3 dimensions. Even with that, it is not easy to calculate the surface area and volume. For higher dimensions, visual representation is impossible. However, we can readily generalize the circle to higher dimensions using algebra. Furthermore, one can use calculus to determine the surface area and volume quite easily in the algebraic representation. Thus, the algebraic representation is superior for these kinds of problems. So, whose understanding is better and more comprehensive? who has really understood what a circle is. One could argue that, despite the convenience offered by the geometric representation, the algebraic representation captures the essence of a circle more comprehensively. A circle's invariant and symmetry properties are better captured in this representation, making it easier to generalize, explain, and reason with, and calculate new properties. However, most importantly, just because Georgette does not, and perhaps cannot, explain and justify her conclusions, it does not mean that she does not understand what a circle is. She certainly understands it in an empirical sense, but her understanding is incomplete if it is not complemented by the algebraic view. Similarly, one could argue that Alice's understanding is also incomplete if she never sees a circle geometrically. Therefore, even in highly precise disciplines such as mathematics, we can have representations that are incomplete. This dichotomy also suggests the exciting possibility that there could exist other representations in high-dimensional spaces that are richer in capturing and revealing important mathematical relationships. This possibility reminds us of the almost magical abilities of Srinivasa Ramanujan, the Indian mathematical genius, for whom scrolls containing the most complicated mathematics would unfold in his dreams. Ramanujan seems to have had access to an abundantly rich representation of mathematics in his mind that was more geometric or visual in nature in the spirit of our discussion above. Therefore, many complex and startling results were obvious to him because he saw them to be true. For him, the new mathematical results did not require proof because they were like points A and B on the circle. They obviously lie on the circumference and therefore needed no proof or explanation. Knowledge representation in LLMs. The enormously successful use of high-dimensional vectors for embedding tokens, for example GPT 3.5 uses 12,288 dimensions, raises an interesting question. Could the LLMs be using a geometric representation rather than an algebraic one for their knowledge internally? Therefore, instead of reasoning, they merely look up in their internal knowledge base to answer queries, somewhat like Georgette. An LLM's performance critically depends on the quantity and quality of data used in its training. The table shows the approximate sizes of the three versions of GPT. As the LLM has more parameters and is trained on more data, its problem-solving capability grows enormously. GPT 3.5 is roughly 1,000 times the size of GPT-1 in parameters, and knows roughly 100 times the knowledge of GPT-1. Studying the evolution of GPT-1 to GPT 3.5 in the context of our discussion above, we find that this is similar to the representation of a circle with more and more noisy data points. Figures 1 and 2 represent the perfect circle, the one with infinite noise-free points. On the other hand, the noisy circle's figure represents different imperfect, incomplete, and noisy approximations of a circle. Generally speaking, GPT-1 is like the first noisy circle, whereas GPT 3.5 is like the third noisy circle. Just as interpolations or extrapolations made using the first noisy circle could lead to incorrect results, the sparse data in GPT-1 made its performance relatively weak. The much denser data in GPT 3.5 resulted in much better performance. In the real world, the knowledge equivalent of the perfect circle is not available for most practical situations. So, what we do is develop useful approximations by training LLMs on enormous amounts of data that tend to be inherently incomplete and uncertain. This results in LMS developing an internal geometric representation of their noisy training data, similar to the noisy circles. Moreover, for many practical situations, the equivalent of the algebraic representation of a circle is simply not available. For example, we cannot write down such abstract equations to model natural language, vision, or game playing. Therefore, for such problems, we are dependent on the purely data-driven geometric model of the world. There are some notable exceptions in the scientific and engineering domains, which we address in the next section. Recent articles from researchers in Anthropic AI and OpenAI shed some light on the internal representations of commercial-grade LLMs. The Anthropic AI team examined one of their LLMs, Claude 3 Sonnet, using a method called dictionary learning to discover patterns in the activation of neuron combinations. When Claude was asked to discuss specific topics, approximately 10 million of these patterns or features were identified. The team found that these features exhibit depth, breadth, and a level of abstraction indicative of Claude's sophisticated capabilities. They developed a type of distance measure between features based on the neurons involved in their activation patterns. This enabled them to search for features that are close to one another. Examining a feature related to inner conflict, they found features associated with relationship breakups, conflicting loyalties, logical inconsistencies, and the phrase catch-22. This indicates that the internal organization of concepts within the AI model somewhat aligns with human notions of similarity. These results resonate with our hypothesis and analysis that the LLMs are using a geometry-like internal representation in a high-dimensional embedding space rather than an algebraic one. In the circle example, the geometric representation readily revealed which points are spatially close to each other, which are further apart, what the subtended angles are, and so on to make reasoning easier. Similarly, in the high-dimensional meanings space represented by the vector embeddings, Claude's internal representation captured the meanings of words and phrases and their relative distances in a geometry-like manner, making it easier to do sophisticated reasoning, such as analogies and metaphors. Claude reasons without actually doing the reasoning, but simply looking up. So Claude understands its knowledge in the sense that Georgette understands a circle. The important question here is the following: what is the algebraic representation of Claude's knowledge? This is possible for simple geometric objects like circles, but is it even possible for complex large-scale data? If not, can we at least develop useful analytical approximations? In this context, some of the concepts and techniques that were developed in the era of symbolic AI in the 1970s and 90s, such as rule-based representations, frames, and ontologies used in expert systems, could be helpful in developing such analytical approximations of real-world knowledge. Recent work shows how this could be done in different applications to develop mechanistic algebraic approximations of the world, to complement the geometric view. For someone who is born blind, it is virtually impossible to imagine what it is like to be able to see the world around him effortlessly, in real time. For him, everything is located after considerable effort, through elaborate searching and feeling for objects, that is, performing spatial reasoning. He will have no appreciation for colors, brightness, or other visual features. He will be amazed at what a person with sight is able to do effortlessly without searching, literally looking up to locate objects and make decisions. The capabilities of a sighted person would appear magical. It is impossible to explain to him how a person with sight sees. Likewise, it is nearly impossible for us to understand how the LLMs see the world in a way that could be very different from ours. In a biological visual system, features are extracted, assembled, and interpreted at hierarchical levels of detail. Similarly, we believe that the LLMs perform picture-like processing and interpretations of the tokens. In this sense, the LLMs seem to possess a mind's eye. Many queries that require considerable effort of searching and reasoning for us would seem obvious and easy, requiring no reasoning or search for them. Like Georgette, the LLMs do not reason because they don't have to. They do not explain because there is nothing to explain. It is interesting to note that our theory of geometric and algebraic representations of knowledge in LLMs is similar in spirit to the cognitive theory of semantics for humans proposed by Peter Gerdenfors. He argues that our minds organize information in a format that can be modeled in geometric terms. We cannot look into the minds of people directly to test this theory. We can only resort to indirect empirical tests. However, we are fortunate to have the ability to observe the insides of LMS. This is what the Anthropic AI results reveal and lend support to the geometric representation hypothesis. From LMS to LKMS for science and engineering. As observed, relying only on a geometric understanding of the world limits the potential of LMs, particularly for science and engineering applications. For example, a self-driving car can navigate impressively through crowded city traffic, but does it know and understand the concepts of mass, momentum, acceleration, force, and Newton's laws as humans do? The car's behavior seems animal-like, similar to that of a cheetah chasing an antelope in the wild. Both animals show great mastery of the dynamics of the chase, but do they understand the underlying physics, classical mechanics, or the underlying math, calculus? The animals do not seem to have that kind of understanding, but they do possess a practical understanding of the domain, which allows them to execute the required tasks well. They possess the know-how of different tasks, but not the know-why. In the parlance of the expert systems era, they possess superficial heuristic knowledge, but not deep knowledge. It is in the area of know-why that humans excel, with their ability to perform abstract symbolic reasoning to develop predictive mechanistic models of the world from first principles. It appears that current LMS have perhaps achieved animal-like mastery of their tasks, but not a deeper mechanistic understanding of the world, as humans do. These deficiencies pose challenges for LMs, particularly in the science and engineering domains. The scientific and engineering domains are governed by the fundamental laws of physics and chemistry and biology, constitutive relations, and highly technical knowledge about materials, processes, and systems. Not paying particular attention to such a treasure trove of existing knowledge seems not only inefficient but also potentially unsafe. The cost of a mistake in movie and restaurant recommendations is not very high. Maybe one loses a couple of hours and a few $100s. However, guessing the wrong decision about a technical operation in a chemical or nuclear plant could lead to potentially dangerous results. These concerns underscore the need for LMS to evolve beyond their current capabilities and incorporate both algebraic, that is symbolic, and geometric representations of the world, particularly for science and engineering. Such hybrid AI systems will be more reliable and interpretable and would also require fewer data to train. We call these hybrid AI systems large knowledge models, LLMs, because they will not be limited to NLP-based techniques or NLP-like applications only. The main challenges that plague current LLMs have been around in AI since the era of expert systems. As heuristic rule-based expert systems emerged in the early 1980s, they were the LLMs of that era. Critiques observed their main failings, such as their shallow understanding, limited generalization, brittleness of behavior, lack of reasoning transparency, poor inference, unreliability, and so on. We find the same old issues resurfacing and some new ones due to the probabilistic nature of the new models in the context of LMS. Since the dawn of AI in the 1950s, there have been two opposing camps, symbolic versus connectionist, battling for their ideas. For nearly 5 decades, symbolic AI dominated the discourse, culminating in the success of expert systems in the 1980s and 1990s. The connectionist paradigm was given a rebirth with the rediscovery of the backpropagation algorithm in 1986, and with the advent of deep neural networks around 2010, it has taken off. Now the pendulum seems to have swung to the other extreme. AI is now dominated by the connectionist paradigm. Although the connectionist camp seems to have won the latest battle for ideas, we believe that, in the long run, AI will be determined by the successful integration of both the symbolic and connectionist ideas. We need the symbolic paradigm to capture first principles-based mechanistic deep knowledge and reasoning, and connectionist representations for data-driven empirical knowledge. The importance of using such human expertise has become evident even in non-technical areas for LMSist. For example, ChatGPT uses human experts' guidance as reinforcement learning, using human feedback. This is reminiscent of the techniques employed in expert systems. Another example of this realization is the development of alpha geometry, which proves mathematical theorems at the Olympiad level. As a neurosymbolic system, it uses a language model in conjunction with a symbolic deduction engine. More is different. In 1972, the physics Nobel laureate Philip Anderson published a highly influential paper entitled More is Different. In it he observes, the constructionist hypothesis breaks down when confronted with the twin difficulties of scale and complexity. The behavior of large and complex aggregates of elementary particles, it turns out, is not to be understood in terms of a simple extrapolation of the properties of a few particles. Instead, at each level of complexity entirely new properties appear, and the understanding of the new behaviors requires research which I think is as fundamental in its nature as any other. That is, it seems to me that one may array the sciences roughly linearly in a hierarchy, according to the idea, the elementary entities of science, X obey the laws of Y. But this hierarchy does not imply that science is just applied Y. At each stage entirely new laws, concepts, and generalizations are necessary, requiring inspiration and creativity to just as great a degree as in the previous one. Psychology is not applied biology, nor is biology applied chemistry. In this sense, Newtonian mechanics and F equals ma can explain the dynamics of a few particles. However, when we have Avogadro's number, which is 6.02 times 10 to the 23rd power of molecules dynamically interacting in a gas, the collective behavior cannot be understood by applying Newton's law, 10 to the 23rd power times. Sure, F equals ma is going on at the molecular level, but there is much more happening that cannot be understood by Newton's second law alone. Physics does not scale this way. To explain the macroscopic phenomena, we need entirely new concepts, such as density, temperature, pressure, entropy, chemical potential, and so on, to predict and explain the behavior of a gas. These concepts are absent at the individual particle level in Newtonian mechanics. We need an entirely new conceptual and mathematical framework, called statistical mechanics, to address this new physics. Similarly, in our opinion, when OpenAI transitioned from GPT-1 to GPT 3.5 and beyond, they created an entirely different beast that is qualitatively, not just quantitatively different from GPT-1. Once again, invoking a physics analogy, it is similar to the transformation from a gas, such as the density of steam at 1 atmosphere and 100 degrees Celsius, to a liquid, such as the density of water at room temperature and 1 atmosphere. As the density increased by approximately 1,000 times, one sees a similar thousandfold increase in parameter size from GPT-1 to GPT 3.5. A liquid is not just a scaled version of a gas. It has entirely different physics. Likewise, the ultra-large language models, such as GPT 3.5 and beyond, are not mere autocomplete engines, but they have new emergent capabilities that require creating a new conceptual framework, similar to the transition from Newtonian mechanics to statistical mechanics. As noted in statistical mechanics, F equals ma is happening in molecular collisions, but the overall physics is much more than and much different from what is implied by Newton's laws. Similarly, in GPT 3.5 and beyond, autocomplete is happening at the individual token level, but the overall behavior is much more and much different. More is different indeed. In conclusion, generative AI has opened up unimagined possibilities in all aspects of human endeavor. It is poised to have a great impact on many aspects of science and engineering. However, to harness its potential safely and effectively, we need to go beyond large language models to large knowledge models, which deeply incorporate fundamental knowledge and human expertise. This requires integrating the geometric and algebraic representations of the world in a new mathematical framework of large knowledge models. Obviously, nature has figured out how to do this using deep neural networks in our brains. Our challenge is to do the same in generative AI systems,